internal flow. And this actually is where I think the semester becomes more interesting for most engineering students. It's internal flow. It's very applicable. Well, first of all, we step back and we talk about the velocity profile for flow in a pipe. We've done this before. So you think about the pipe. You think about the center line of the pipe. That's a bad looking center line, isn't it? You characterize the radius R going from the center out to cap R, the inner radius of the pipe. And we're interested in predicting the fluid velocity profile. Where will it be maximum? In the center line, right? And now what we want to do is remind us before we do a derivation, if I did have the velocity profile given, if I was given u as a function of r, then how could I get the average velocity? Well, the average velocity, v average, is 1 over the area, the integral of u dA. Remember that? We've done a couple of those cases. And so a lot of times u will be u max times 1 minus r over cap r squared. That's for laminar flow. That's for laminar flow, okay? And when you compute the average velocity for laminar flow, where this is the maximum at the center line, the average is 1/2 u max. It's 1/2 the maximum speed. So if you tried to plot it, go out here, cut it in half, and there's your average velocity. Okay? All right, we're also familiar with the volumetric flow rate concept. The volumetric flow rate, A times V, the cross-sectional area times the average velocity, will give you the volumetric flow rate. And then if you multiply that by the mass density, AV, you'll get mass flow rate. So all those concepts I think are pretty familiar. Okay, here's a problem. We have the velocity profile in a pipe of radius r is given by this profile, that equation. Determine the average velocity in the pipe. So if you were given that problem, you would want to do the average velocity is equal to 1 over the area, pi r squared, times the integral of u max, the equation that's given, 1 minus r over cap r, all to the 1/6 power, times dA, which is 2 pi r dr. Let's bring this r squared in here and there, and then let's cancel the pi, and so V average is equal to u max, take that integral outside the integral, times the integral of 1 minus x to the 1/6 times x dx, where x goes from 0 to 1. And it's solved on the next page. Wolfram, it's the integral I wanted to do, and it comes back almost 80%. So the average is almost 80% of max. Okay, so this velocity profile, if I plot it, it's more like a turbulent profile. It'll be flatter, and the average will be 80% of the maximum, which is the maximum's not that different from in the middle, in the core. It's pretty flat in the core, that velocity profile. Okay. What's the difference between laminar flow and turbulent flow? Laminar comes from the word like layers. So if you have a layer of fluid going down the pipe, and it's kind of the blue layer here, the purple layer here, and the black layer here, later on down the pipe, if you take a look, the blue layer is still there, and the purple layer is still there, and the black layer is still there. But if it's turbulent, the little chunks of the blue that started here may be over here, and vice versa. The little chunk of black here could be over there, and so they change the location. They're mixing. Instead of staying in their relative layers, they mix a lot. That's turbulent flow. Osborne Reynolds was the one who studied it. Take a look at his years of his life. So he studied it a long time ago, didn't he? And so around late 1800s, he was studying this phenomenon, and he would have a tube that he could see inside. He'd flow water in it, and he'd have introduce a little dye, and that dye he would watch. And if it stayed right there, it was laminar flow. But if he turned the flow up in speed, the speed was going faster in the pipe, then that would start to go and mix up. And he said, okay, now I have turbulent flow. So they honor him still with coining the term Reynolds number, which is the ratio of inertial to what? To the viscous. Viscous, inertial to viscous. Did I say that on the FE exam, you want to take the FE exam after you get your undergraduate degree or the last semester of your undergraduate degree in mechanical engineering so you can begin that process to become a professional engineer, right? Well, you can almost anticipate in the fluids section probably a multiple choice question on the Reynolds number is a ratio of what to what. And they'll have gravitational to viscous and inertial to gravitational, etc. But you need to look for the one where it's inertial to viscous. I'd say probably 1/3 of the time that question's on the exam. All right, the critical Reynolds number. So what he found was for slow flow, for small Reynolds number, when it was below about 2,000, it stayed laminar. He could predict it. But if the Reynolds number was above this critical number of maybe around 2,000, some people report it 2,300, some people 2,100. If you just want a rough number, 2,000. Okay? If you're above, then you can anticipate turbulent flow. Why isn't it just such a fine number you know it to 3 or 4 significant digits? Because other factors come into play. Is there a little vibration in the room where the pipe is? A little machinery running? That helps it promote turbulence, a little vibration, background vibration. So you have to have a lab which has a very calm, no vibrations, no motors running, even the second floor, 2 floors over in the basement, so you have no vibrations. Even if you as a human can't feel it, maybe it's there in the background, in the machinery, it'll be reflected in the flow. So these are approximate, and so you can experimentally, if you try hard, keep it laminar to higher critical Reynolds number, maybe 2,500. But there's a cutoff around 2,000, 2,300, somewhere in there. So what about non-circular pipes? Let's say you have ducts or an ellipse, professor. Do they really have ducts and ellipses like that, rectangular for airflow and water flow? Yes, they do, especially for airflow systems. And a lot of reason is you typically put the airflow in the ceiling. So between the bottom of the floor above us and this drop ceiling, there's a lot of electrical and plumbing, and there's a lot of HVAC, okay? And they need to fit it into that tight space. The architects like to have that tight space small. Mechanical engineers like to have it large. And the contractor that installs all that stuff likes it even larger. And if you look at the AET, it's huge. You could probably stand up there. All right? But a lot of commercial buildings, it's very narrow. And so they need to move a lot of air in ducts, and so the height is the restriction. So they typically get rectangular ducts or elliptical ducts. And when they were building that building, the BSE, I saw, yeah, they had some big sheet metal, aluminum, not aluminum, sheet metal elliptical ductwork that was being installed. So what you do is you introduce a hydraulic diameter in order to compute the Reynolds number, because the Reynolds number is based on the diameter of the flow. The equation is 4 times the cross-sectional area divided by what we call the wetted perimeter. The wetted perimeter is just this perimeter for either elliptical or the rectangular ducts. Okay? And the cross-sectional area is just what you might expect. It's that cross-sectional area for the flow to go through. So let's work it out. What is the hydraulic diameter for a duct of height A and width B? Well, the cross-sectional area would be A times B, and the wetted perimeter would be 2A plus 2B. Right? And so you can stick it into the equation and you'll get 4A times B divided by 2A plus B. Maybe you reduce it a little bit, but you're stuck. There it is. Okay? You can't really simplify the equation much more than that. What happens if you said, I want you to compute the hydraulic diameter for a nice circular duct? Does the hydraulic diameter give back the actual diameter? And so the cross-sectional area is pi d squared over 4, and the wetted perimeter is pi d. And so the hydraulic diameter for the round circular duct is equal to 4 times pi d squared over 4 times pi d. Oh, look at that. Isn't that nice? The hydraulic diameter is the physical diameter for a round duct. It's pi d squared over 4. That's all. The equation is 4ac over pw. Yeah. What you have to do is you have to look for the equations for elliptical and some other, or work them out. Okay, work them out. You get the hydraulic diameter. What do you do with the hydraulic diameter? You can compute the Reynolds number, and then you can determine if you have turbulent or laminar flow. In most engineering applications, you want turbulent flow. Laminar flow is too slow. You're not moving enough fluid in that pipe. Okay? There's a few applications where it's laminar, but mostly it's turbulent flow. But we can't analyze turbulent flow analytically like we can laminar flow. So we beat up laminar flow. But you may come out of this class and have a false impression. Wow, we studied and all these equations for laminar flow, and we spent all the time deriving these equations. They must have a lot of laminar flow out there in applications. Nope. A lot of turbulent flow. All right. There's another diameter. It's called the equivalent diameter. It's not equal to the hydraulic diameter, and you really want to avoid it. But what you would do is, it makes sense. It's not going to be that tremendously bad, but you would do this. You would say that is a rectangular duct. What is the equivalent diameter for the same area? This equivalent diameter, D equivalent, that gives me the same area as that rectangular duct. So you'd have like pi D equivalent squared over 4 is equal to A times B. So this diameter equivalent is equal to A times B, 4 divided by pi square root. Is that the same as this equation, this hydraulic diameter? Compare. Are they the same? Is the equivalent diameter equal to the hydraulic diameter? No, it's not the same. So it's a little different. It's not going to be tremendously a big error, but you really want to avoid the equivalent diameter. Just use the hydraulic diameter. True? Got it. Ready to solve a problem? So they have airflow. They give you the temperature so you can get the density of the air and the viscosity of the air. It's through a 5 centimeter by 8 centimeter cross-sectional rectangular duct at an average velocity of 4 meters per second. Determine the Reynolds number. And so you want to use Reynolds number as rho V hydraulic diameter, because we don't have a round duct. We'll use the hydraulic diameter over mu. And we know rho and V and mu, just need to get that hydraulic diameter. It'll be the, we just did the equation for it. If you calculate the hydraulic diameter, it comes in at 6.154 centimeters, giving us a Reynolds number of 16,700. Now that you've calculated the Reynolds number, Is it laminar or turbulent? It's above the critical?
Yeah.
It's turbulent flow. Okay. Pretty straightforward, I hope. Entrance region. Well, we are going to spend a lot of time analyzing fully developed flow in pipes. But whenever you have the beginning of a pipe, you have a region in which the velocity profile isn't fully developed. It often is very blunt coming in, and later it starts to develop such that the presence of the walls are felt further and further into, and then finally it'll feel the effect of the walls throughout. And there's some length where you have, it's now, the entrance effects are done, and now beyond this, it's all fully developed flow. How big is that entrance region? Is it important in a lot of calculations? Well, it could be, but it's where the velocity profile is being developed, okay? They call it hydrodynamically. It's developing, it's changing the velocity profile, okay? So out in this region, it's hydrodynamically fully developed. Okay, you can think about a boundary layer. It's growing the boundary layer, and when the boundary layer from this side and that side, they coalesce in the middle, it's fully developed.
So fully developed means that reached the maximum velocity?
Yeah, it means that as I continue down and I'm not changing the diameter of the pipe, okay, that the velocity at any radius stays the same. So the velocity in the core right at the center line, it's not accelerating anymore. It did in the entrance region, but not when it's fully developed. Okay, so it's not speeding up anymore or slowing down. What happens is when it's in the developing region, the flow near the wall slows down. The flow in the middle speeds up a little until it gets to the right profile. Well, it has an effect on the profile of the flow in there. And so a lot of times when you have flow, this is entrance, but let's say I have a bend. Let's say it's a mitered bend. You know, ducts, a lot of times they'll do that. They'll just miter them together, and they put no turning vanes in there. Without turning vanes, you'll typically get a flow separation region right there when the flow is going this way. And if you wanted to come in and do a takeoff on a duct over here or a duct over there, that being so close to that disruption might have a significant impact on what comes out. Okay, so a lot of times they'll have some rules of thumb, like after a major change like that, make sure you go down a long enough distance so it's now back to fully developed or close enough to it. There are a lot of practical implications of this about, you know, being fully developed. Okay. Also, spins of flow. There's a lot of practical implications of the way it's spinning inside of a duct or even inside of an automobile engine. Okay. Or into a fan. Is it spinning the way to help catch it and throw it into the fan, or opposing the spin? So anyway, what is this entrance length? How long is it? Well, the entrance length is about 10 diameters if it's turbulent. That means, you know, if it's going to be turbulent, it's going to develop pretty quickly, and 10 diameters is a rule of thumb, and it's a lot of textbooks. It's pretty well agreed upon, 10 diameters. But if it's laminar, it's a little more complicated. It's 1/20th of the Reynolds number times the diameter. That's if it's laminar. So you say, well, it depends on the Reynolds number. Let's say the Reynolds number is 1,000. Am I laminar or turbulent if the Reynolds number is 1,000? Laminar. Just put 1,000 in there. How many diameters is that then? If I put 1,000 right here, I divide by 20, what do I get? 50 Ds, don't I? So it can be a lot longer than 10 diameters, 5 times longer. let's say I put in 2,000 and it just is going to stay laminar. It's 100 Ds, 100 diameters. But that's about the extent of it. That would be the most, because if you go over as you increase the Reynolds number, isn't the entrance region increasing for the laminar flow? But if you increase it above the critical, it's no longer laminar, it's turbulent. So your entrance region is a limit 50 diameters. But mostly we have a lot of turbulent flow, 10 diameters. A lot of times also in pipes and flows, if they have a bend or entrance region and they're trying to do some ultrasonic flow measurements, they specify how far you have to have where it's straight before you put the instrument in there. Some meters. And guess what? If you go out there and practice, you'll find that the company that installed that meter, they hired that tech. That tech said, put that meter in. He went up there and he put it in. He didn't read anything about the meter and how many standoff, how many diameters since a recent bend or anything. And so there's a lot of equipment, I hate to say it, out there that probably are not in the manufacturer's recommended, straight section of the pipes. It's just, they got to fit it in, package it in. Laminar flow in pipes. So let's get to a differential equation, right? Isn't mechanical all about being a good mathematician? Right? Mechanical engineers, it's just about mathematics? No, you may come out of your undergraduate education feeling like that, but it's not all about mathematics. But there are a few things you need to really apply math to and apply the calculus to. This is one of them. You don't leave school without knowing this and being able to do this, right? Analyze something as simple as the actual anticipated velocity profile and laminar flow in a pipe. So how do we start for laminar flow in a pipe? Consider a pipe, the center line, and we're going to focus our attention on a section that looks like this. Okay? It's a little box, but the box goes all the way around the pipe, 360. Okay? It has pressure acting on this surface, pushing it in the positive x direction, pressure on that surface, pushing it in the negative x direction. And we're going to do a force balance on this section of fluid in this box, right? Okay, so the first is going to be at this location x and that location x plus delta x. So we have the pressure at x times that area. Now try and envision it. It's a ring going around. So it's 2 pi r dr, or delta r. So it's at the location r and delta r. Does that make sense? That's moving it in the positive x direction, minus, because it's in the negative x direction, p at x plus delta x times 2 pi r delta r. So those are two forces on the ends. They're due to pressure times that little area of that ring on the ends. Now we also have viscous forces. The flow in the middle of the pipe's going faster, so it's trying to pull the fluid on that side of the ring, the inner side of the ring, in the positive x direction. The fluid on the outside is slower. It's trying to make it move in that direction. So you see my little direction associated with the shear stresses? So let's go ahead and say in the positive x, we're going to have the viscous shear stress, tau, at what location? R, times the area. What is the area? 2 pi r delta x. Does that make sense? Is it 2 pi r delta x? Can you see that? Okay, that's in the positive x. Hit my wire. All right. Minus on the outside right here, that's equal to tau at r plus delta r times 2 pi r plus delta r times delta x. Some of those forces, 2 normal, 2 shear stresses, okay, acting on that little area or volume. The sum of those have to equal to 0. Fully developed flow. So we take our equation and we divide by delta x delta r, delta x delta r. What cancels? The delta r's here. What cancels over here? The delta x's. All right. And so we pick up a minus. I'm going to pull the 2 pi's out. 2 pi. I'm going to pull the r out. dp dx. Does that make sense on that one term? Why do I have the minus? Because I needed to put that like this. Right? And so I get that. And then over here, I'm going to pull out the 2 pi. I don't pull out the r because I have a r and tau at r, and then I have tau at r plus dr times r plus dr. So what we have is the derivative with respect to r of tau r, the shear stress, times r. Well, what is that viscous shear stress? It's given by somebody's law of viscosity. Newton's law of viscosity. What was it? Mu du dr. And so we can substitute. Also, this was a minus sign. So since they're both minus, turn them into positive. All right. So I'll have to scoot down a little bit. Can we get rid of the 2 pi's? Sure. And so we're left with 1 over r, derivative with respect to r, of r times mu du dr is equal to minus dp dx. I know I did a lot, and I did it, maybe I could have done it in more steps, but did you follow it? Did you follow? So what is this mu? Viscosity. And what is this u? Velocity. And we're looking to find u as a function of r. Now, as I look down the length of the pipe, the pressure as I go down the pipe, is the pressure decreasing as I go down the pipe? Or is the pressure increasing as I go down the pipe? This is the direction of flow in the pipe. What is the pressure doing in the direction of flow of the pipe? Going down or going up or what? Real flow in a pipe. Help me. It's going up or down? It's going down, right? So the pressure is going down. Now, it's fully developed flow. Do you think it's going down linearly, or is it going down, you know, some exponentially, or how's it going down? Linearly, it's fully developed. So the pressure drop, you know, for every foot or every meter is the same for the next meter, for the next meter, for the next meter. It's fully developed flow. So this is a constant right here. And it's a negative of a negative entity. This is negative by itself. So the negative of a negative, this is all a positive constant. Make sense? Okay. So I want to solve for u as a function of r. It's a differential equation. I have on the left-hand side, embedded in that 2 derivatives, u is a function of r. On the right-hand side, it's a constant. So I separate and integrate. So what I'll do is I'll say r mu du dr is equal to negative dp dx. Sometimes I put the parenthesis on that. You know, it's like keep the negative with the dp dx because then I know that what's inside the parenthesis right here is a positive constant. Some books don't do it, but there you go. And then I bring over here r dr. I separated. Now I go ahead and integrate, and I'll get r mu du dr equal to negative dp dx times 1/2 r squared plus a constant of integration. Stop me if I make an error. What do I do next? Separate. So I'll bring over this, I'll divide everything by r, and then I'll be able to cancel there. I'll have to cancel 1 there. And this mu I can bring over, so I'll get 1 over mu. And when I bring the 1 over, I just change a constant. You know, it's just a different constant of integration. So now I have du dr is equal to 1 over mu negative dp dx times 1/2 r plus constant of integration over r. True? Separate and integrate. Du equal to 1 over mu negative dp dx 1/2 r dr plus constant 1 over r dr. Integrate. U equal to 1 over mu dp dx 1/4 r squared. Did I do that one right? I see a thumbs up. Good. Plus C1 natural log of r plus another constant. I have at a second order equation, I have 2 constants. What are my conditions? My boundary condition are that u as 0 is equal to the maximum, u max, and u at cap r is equal to 0, no slip. So when we solve for it, we get, oops, I need to introduce a new page. New page. Insert new page. All right. So when we solve for it, we get u is equal to u max times 1 minus r over cap r squared, where u max is given by, well, let me do it another way. 2 times u average times 1 minus r over cap r squared, where u average is equal to r squared 8 mu minus dp dx. I've solved for those constants of integration. One of the constants of integration, C1, is 0. The other constant works so I get the shape here. And I can express it as u max or 2 times u average. That is the same as u max. So this is my profile. It's quadratic. And this is the average, how it's related to the viscosity, how it's related to the radius, and how it's related to dp dx. Somebody says, I don't like working with radius. All of our pipes, we talk about diameter. Good. 2 radius is a diameter, right? Square it. So what happens is I get a 4 times 8, 32. Diameter squared, mu times negative dp dx. See how we switch radius to diameter pretty easy? All right. Now, somebody says, let's do this. let's bring negative dp dx over here and put an a length here. Okay, and so now we're going to have 32 times viscosity times length times let me do this, diameter squared, length, oops, not diameter squared, it's length divided by diameter squared. Did I do that right? I'm trying to look at it. That makes sense? Okay. All right. Okay. Now, if I multiply by a density and a density, okay, and I multiply by, oh, I left off the average speed, didn't I? That's what I left off. Where did this go? U average. It needs to be right here, U average. All right. If we multiply by U average over U average, just like that, we didn't change anything, but we're starting to group things up. Okay. And let me have this D and put another D, split the D's. All right. Okay. What is rho V D over mu? That's right. So what we pick up is we pick up the Reynolds number right here. Okay. Right. Let's do this. So we have what is, if I put a 1/2 right here and a 1/2 right there, what is 1/2 rho v squared? Velocity pressure. The velocity pressure, right? So it's equal to 64 L. I'm sorry, get rid of that L. Just get rid of the L's. Velocity pressure. All right, minus dp dx. No, I need that L. I'm sorry. And then L over D. L over D right there. All right. I know it's taken me a while, but guess what? Let's flip this over. Negative dp dx times d over L. Yeah. L times d over L. Divided by the velocity pressure 1/2 rho v squared. That's equal to 64 over the Reynolds number. Yeah.
There is another L and the second.
This one right there. That's right? Yeah. Okay, so we're there. Now, what is negative dp dx times L? We talked about the pressure is dropping right here. So if I go from a distance 0 out to L, it's the change in the pressure. It's the pressure drop or pressure loss or dP, right? So right here, this is the pressure loss times diameter over length divided by the velocity pressure, and that's equal to 64 over the Reynolds number. This term is given a name. It's the friction factor, F. So for laminar flow, we make the great conclusion. I'm not the first to do it. It was done way back. I mean, look at the years that Reynolds lived, right? The friction factor is equal to 64 over the Reynolds number for laminar flow. So embedded in that friction factor is the pressure drop, or the pressure loss, or the pressure gradient, whatever way you want to talk about it. Okay? And you have just 64 over the Reynolds number. Okay? So we've shown two things: how to calculate the pressure loss for laminar flow in a fully developed laminar flow in a pipe. The pressure loss is going to be calculated by unraveling friction factor is equal to 64 over the Reynolds number. Okay, so this unraveling, that was delta PL, or pressure loss, whatever you want to, however you want to write it. I guess I should be consistent. PL times L over D divided by 1/2 rho V squared. So it's the friction factor times this is really L over D. This is D over L. Yeah, that's D over L right there. So now it's L over D times 1/2 rho V squared. And so for laminar flow, you can replace friction factor by 64 over the Reynolds number. Let me ask a question. What are the SI units of the friction factor? They're the same as the SI units for the Reynolds number. What are the SI units for the Reynolds number? Dimensionless. They're the same as the SI units for the drag coefficient. See, all these dimensionless parameters are dimensionless. The friction factor is a dimensionless parameter. L over D is also dimensionless, is it not? But we're going to get pressure from the velocity pressure. The units in that come from the velocity pressure. So your pressure loss is proportional to your velocity pressure, 1/2 rho V squared. That friction factor, F, that's the definition of it right here. Wrote it backwards. So now we have an easy way of putting in for pipe flow that modified Bernoulli's equation. Remember? We said, oh, we can, let's do a pipe analysis. We'll come down and we'll do a bend, and then we'll do a restriction, maybe a smaller pipe or something like that. Maybe put a turn here, and then we'll come over and we'll put a valve in or something like that. Okay? For each of these straight runs right here, this is, let's say, run 1 with length 1, diameter 1. This run right here goes length 2, diameter 2. This one, length 3, diameter 3. Okay? What you do is you'd have, starting the equation, Bernoulli's equation, go like this, all the way through, modified Bernoulli from 1 to 2. You would say, okay, the pressure at 1 plus 1/2 rho V1 squared plus rho GZ1 plus any pressure gains equal to the pressure at 2 plus 1/2 rho V2 squared plus rho GZ2 plus any pressure losses. Any pressure losses. And so we'll have the pressure loss in run 1, the pressure loss in run 2, the pressure loss in run 3. Okay? And how would you get that pressure loss in run 1, or that leg 1? That equation. It would be friction factor in that leg, the length 1 to the diameter 1 times the velocity pressure in that leg. Now, if you don't change the diameter and you don't divert some flow out of your pipe, then the velocity pressure in a lot of those legs in series will be the same. Now, later we'll talk about adding minor loss coefficients due to elbows, due to restrictions, due to valves, and we'll just add terms. We'll have an additional pressure loss due to the elbow. We'll have a pressure loss term due to the valve. We'll have a pressure loss term due to restriction. I'm running out of room, see? But the pattern is there. Does the pattern make sense? Hopefully. So now you can calculate for laminar flow pressure drops in straight runs when it's fully developed. And the pressure drop equation, the pressure loss equation, is F L over D times 1/2 rho V squared. How about turbulent flow? Might get right away to turbulent flow. Well, it's very disorderly. There's a lot of rapid fluctuations in the flow. It's swirling, and it's well mixed, okay? You have a very blunt velocity profile, and they've been studying it for a long time. There's an equation, the Colebrook equation, that came out, look how long ago, right? 1939. It's a long time ago. And what do they have here? F. What is F? Friction factor. And they have Reynolds number, turbulent flow, it needs to be over 2300 for turbulent flow. And they have the roughness of the pipe, so that a lot of times they don't have smooth pipe. The pipe has some roughness, and they characterize that roughness, and they compare it to the diameter of the pipe. So this ratio is a roughness to the diameter of the pipe. The next slide will show you some typical values for roughness. If you have PVC pipe, like you buy it, a lot of water lines, it's very, very smooth. Roughness, you might as well just throw it out. 0. So small. If you have drawn copper tubing, we have a lot of water in PVC and a lot of water in drawn copper tubing. It's very smooth. Throw it out. But if you have cast iron, right, or what they say iron pipe, it's not cast, it's rougher, especially if it's been in service for a while and there's some erosion, corrosion, and deposits. So then you would have to account for it. And years ago when they were doing this, they also had concrete pipe and clay pipe. They would run fluid, water, and flow through that, right? So that you had a larger roughness. But you can see what you have is, as a function of Reynolds number, you could calculate the friction factor. The only problem with the Colebrook equation, it's implicit. So in '83, Holland came up with an equation where it's explicit, and it's just as accurate. So you just say, give me the Reynolds, give me the roughness, and I'll give you the friction factor. Kind of like inputs on the right, output on the left. There's also a Churchill equation. It's even better. I didn't even show it to you, okay? But you plot it. You could plot this in the Moody diagram, one of the most famous diagrams in all of fluid mechanics. And they plot on the y-axis the friction factor, F. They plot on the x-axis the Reynolds number. They plot in a region, it's called laminar flow, and look at the equation they give, 64 over Reynolds number. So in the laminar flow region, it has to be below around 2,000. Here's 1,000, here's 2,000. They stop it, you know, they're not going to plot it above around 2,000. They show you what the friction factor is doing. It's a straight line on a log plot. Isn't this log scale? And what is this scale? Can you see its log? And it has really a slope of -1 on a log scale plot. Then they have this transition region. It is not a crisp demarcation between them, laminar and turbulent. But somehow, if you're in the turbulent, now you're at this Reynolds number, that Reynolds number, you're clearly turbulent. Depends now if you're in a very smooth pipe or if you have some roughness, relative pipe roughness. So this is a curve of constant relative roughness. This is a curve of an even more rougher pipe, etc. A lot of our problems are right down in this region. They're turbulent, but they're relatively smooth pipe. A lot of our problems in engineering, okay? So if you really go out to really high Reynolds number, then you have to be cautious, because even what may seem to be smooth isn't all that smooth when it's really rough. I mean, really high Reynolds number flow. Because this is relative roughness is getting smaller. So here's our friction factor. They plot it right here, or print it right here. It looks like it's garbled up, but we already covered it. It's the pressure loss, right? Times D over L 1/2 rho V squared. Okay. And here are some roughnesses in millimeters for different material. Concrete, coarse concrete pipe. They put it in here because it was done in the 30s. There's just not a whole lot of coarse concrete pipe and water flow. Plastics kind of come into play, right? There's a lot of plastic pipe out there, and we use it a lot. But you see some cast iron old, sewer old, steel rusted, old water mains, anyway. But they don't show you, here's drawn tubing. That's pretty low, isn't it? Drawn tubing, like our copper tube. You buy it in straight line sections, or you can unroll it in a coil. It's do a lot of services to your home, and a lot of flow in your house is in copper, as well as the PVC, okay, which are all pretty smooth. All right. Let's see. I wanted to get that far. Do you have any questions for me? Do you want to solve a problem? Okay. So water flows at 5 degrees C. At that temperature, we can look up density and viscosity. Through an 8 millimeter diameter pipe at a rate of 1.15 liters per minute, the flow is laminar. What is the velocity of the water in the center of the pipe? How would you calculate the velocity of the water in the center of the pipe? Is that the average velocity? It's 2 times the average velocity. The average velocity is half of the center line velocity, right? But what is the velocity in the center if it's laminar? So you'd say the velocity in the maximum in the center is equal to 2 times the average, right? So you're given the AV, the volumetric flow rate, 1.15 liters per minute. Right? Yeah, you got to worry about your 60 seconds, etc. But what is the average then? Is it AV, the volumetric flow rate, divided by the area? Yeah. And so this one's known. What's the area? Area is just pi d squared over 4. For this problem was 0.76 meters per second.